Assalamualaikum and hi everybody. Now I will talk a little bit about the channel coding. Channel coding refers to the class of signal transformations. It is designed to improve the communications performance by enabling the transmitted signals to be more reliable, even though affected by various channel impairments such as noise, interference, and fading. Channel coding can be partitioned into two areas. First is waveform coding or signal design coding, and the second one is structured sequence coding or structured redundancy. The waveform coding deals with transforming waveforms into better waveforms to make the detection process less subject to errors. Meanwhile, the structured sequence deals with transforming data sequences into better sequences, having structured redundancy, or it is called as the redundant bits. Okay, now let's go for the waveform coding. Waveform coding procedures transform a waveform set, which represent a message set, into an improved waveform set. This improved waveform set can then be used to provide improved probability of error compared to the original set. And the most popular of these waveform codes are orthogonal codes and bi-orthogonal codes. So now let's go for the orthogonal codes. Okay, to produce an orthogonal code, we will consider B as basic metric, as this one. Okay, after that we will arrange it as this matrix where we have matrix B in the first quadrant, followed by the same matrix B in the second and third quadrant. Meanwhile, for the fourth quadrant, we have complement of matrix B. Now, let's see, for example, okay, if we consider a 1-bit set encoding. Our B can be either bit 0 or 1. However, in this example, we consider B as matrix H0 or bit 0. A 1-bit data set can be transformed using orthogonal code words of 2 digits each, described by the rows of matrix H1 as follows. Okay, you can see from bit 1, it is now encoded bit 0. Okay, with considering that the B is 0, so we have 0 the first quadrant, the second quadrant 0, and the third quadrant also 0, but the fourth quadrant is the complement of 0, which is 1. Now, if we consider the second example of 2-bit data set encoding, we can extend the foregoing set both horizontally and also vertically, which create the matrix H2. So what we can see here, if the B is considered as H1 as what we got from this example, so now with the 2 bits data set, we can also encode it using the same concept here, where this is the B in the first quadrant, the second B, and also the third quadrant also as B, but the fourth quadrant we have the complement of B. So in this case, the data set 00 is now encoded to 0000, while 01 is encoded to 0101, and so on and so forth. Okay, we continue the same construction rule to obtain an orthogonal set H3 for a 3-bit dataset as here. Okay, so you can see that this H3 actually obtains from the H2 as the B, okay, and the complement for the fourth quadrant. In general, we can actually construct a code word set HK of dimensions 2 to the power of k by 2 to the power of k, called as a Hadamard matrix for a k-bit data set from the HK-1 matrix, as what you can see here, where the K is the number of bits. So if we consider the probability of bit error for orthogonal code, it is given by this equation, where it is affected by the number of bit K or also the number of M. M is equals to 2 to the power of K. So now let's go for the bi-orthogonal code. A bi-orthogonal signal set of M total signals or code words can be obtained from an orthogonal set of M over 2 signals by augmenting it with the negative of each signals as this one. Okay, for example, let's say our M is A. So in that case, we are considering to encode the 3-bit dataset where the relationship of K and M is here. K is the number of bits, M is the number of total signals of all the code words. So in this example, okay, we can now use the concept of orthogonal to produce half M, or in this example, 4 signals. So if we have 1, 2, 3 and 4 signals here, it is obtained by using the concept of orthogonal code. After that, we can complement the H3 here, okay, and we will get the rest of the other 4 signals which are at the bottom here. Okay, so we can see, for example, that the data set of 0, 0, 0 is now being encoded to 0, 0, 0, 0. Meanwhile, for encoding the 1, 0, 0, it is given by the complement of 0, 0, 0, 0, which is 1, 1, 1, 1. Now, let's go for the probability of bit error. For the bi-orthogonal code, it is given by this equation, where it is also affected by the number of signals, or M. If we compare the both orthogonal and bi-orthogonal codes, we will see it as this example. If I take data set of 100, the orthogonal code will give me a code word of 00001111, while bi-orthogonal code is only 1111. What we can see here, for the same dataset, the bi-orthogonal code requires 1/2 as many code bits per code word over an orthogonal code. So, the bandwidth for bi-orthogonal is 1/2 the requirements for comparable orthogonal codes. We can see here that bi-orthogonal code is much better in terms of the bandwidth consumption. By the way, we still need other more structured code words that can give us more hint about the status of our received signals. In other words, waveform coding can only guarantee that the received signal less prone to errors. However, how do we know if errors still exist in our received signal? That is why the structured sequence coding is introduced. So now let's go for the sequence coding. The structured sequence coding transforms data sequence into better ones having structured redundancy. It can work in 2 ways. First is automatic repeat request, which only detects errors of the received signals and retransmit the received signal back to the transmitter. The second way is known as forward error correction, is by detecting errors and at the same time doing the error correction on the received signals. As a basic concept, we only concern on the characteristics of these 2 ways. So this is an example on how ARQ works. Okay, let's consider a message bit 1001. With the ARQ, a parity bit that ensure the number of bit 1 is even is added to the message bit. So we will consider that at the receiver, the message has no errors if it can maintain the number of bit 1 as even. If the signal is received at the receiver containing odd number of errors, then the number of bit 1 will be detected as odd number. As we can see in this example, we have 3 bit 1s, which is odd. So in this case, the receiver will ask for retransmission as it detects the errors. So what we can see from this approach is only odd number of errors can be detected but cannot be corrected. Alright, so now let's go for the FEC. Using FEC, more parity bits are required to be added to the message for encoding process. The parity bits are arranged depends on which FEC code that we use. Once the code word signal is received at the receiver, the decoding process will detect the location of error, and after that, it will do the error correction by toggling the error bit. In this example, one error can be detected and corrected. So we can see now, the difference between these two approaches, that the advantage of ARQ is error detection requires much simpler decoding equipment. However, the information needs to be retransmitted when the errors occur. But in certain applications, we must select the FEC as the error correction if reverse channel is not available or ARQ delay will be excessive and the expected number of error without correction will require excessive retransmission. So that's actually how we can see the basic concepts of the channel coding, and I hope that you can learn a little bit from this video.